Hi everyone, welcome back to my channel. In our last video, we have discussed about the concept of crystal field theory, and there we said the crystal field splitting in three different kinds of geometrics, that is octahedral, tetrahedral and square planar complexes. In case of crystal field theory, the most important factor is the crystal field splitting energy, which is also called as crystal field stabilization energy. It is the most important factor that we are supposed to learn, and it is most frequently asking question in all the competitive examinations such as GATE, NET, KCET as well as in IIT JAM examinations. So now we shall focus on what is the exact meaning of this crystal field splitting or crystal field stabilization energy and how we are supposed to calculate. Okay, and if you know we know that under the influence of approaching ligands, the d orbitals of the central metal ion will get splits into two sets of orbitals having different energy, and we call that as crystal field splitting. When the 5d orbitals such as dxy, dyz, dxz, dx square minus y square and dz square, when all the 5 degenerate d orbitals splits into two sets of orbitals with respect to the spherical field, for which we used to take the energy is equals to 0, the energy difference between the two sets of d orbitals that will be produced due to crystal field effects, that is due to electrostatic repulsions between the ligand electrons and the electrons present in the d orbitals, we used to get two sets of d orbitals, right? The energy difference between the two sets of orbitals produced as a result of crystal field splitting is actually called as crystal field splitting energy, simply abbreviated as CFSE, that is crystal field splitting energy. And the crystal field splitting energy is simply represented with the symbol delta. Delta is a symbol for crystal field splitting energy, and it is however measured in terms of an arbitrary parameter called as dq. It's an arbitrary parameter which is used to express or to measure the value of crystal field splitting energy. And the magnitude of this crystal field splitting energy in general, it is taken equals to, that is delta, that is almost taken equals to 10 dq. So if it is if the crystal field is splitting in case of tetrahedral complexes, delta is suffixed with T, and if it is octahedral complex, delta is suffixed with O. But the exact value of the crystal field splitting energy delta is actually depends upon the geometry of the complex as well the nature of the ligands that are approaching the central metal ion, as well the number of ligands approaching the central metal ion. That means whether the complex is octahedral or tetrahedral, and whether the number of ligands that are approaching the central metal ion are lesser in number or greater in number, or else the nature of the ligand, that means whether the approaching ligand is a strong ligand or weak ligand. All these factors will comes into picture in measuring the value of crystal field splitting energy. And the stability of the complex, which is formed by the combination of central metal ion and the definite number of ligands, is quantitatively measured by knowing the value of crystal field splitting energy, and hence we used to call that crystal field splitting energy as crystal field stabilization energy also. So I repeat, crystal field splitting energy is used to measure the stability of the complex compound formed, hence we call that crystal field splitting energy as crystal field stabilization energy also. And simply we can define the term crystal field stabilization energy as the lowering in the energy of a transition metal ion in a given ligand environment due to crystal field effect. That is, when ligands were added to the central metal ion, the electrons will go and accommodate in the d orbitals, and due to accommodation of the ligand electrons in the d orbitals of central metal ion, if the energy of the central metal ion got decreased, then greater the decrease in the energy of the central metal ion, more will be the stability of the complex which is formed. So thereby, by knowing the energy difference between the two sets of d orbitals, which is happened due to crystal field effect, that means the splitting of d orbitals of metal ion due to electrostatic crystal field potential of the ligand, nothing but electrostatic repulsions. So that we call as crystal field effects. And due to crystal field effect, the energy of the transition metal ion, that is the central metal ion, will get lowered. So greater the lowering in the energy of the central metal ion, more stable will be the complex. So this is the way how we can judge the stability of a complex compound formed just by knowing the magnitude of lowering in the energy of the transition metal ion, and that what we call as crystal field stabilization energy. And now we shall look over into the calculation of crystal field stabilization energy in octahedral as well as in tetrahedral complexes. Firstly, we shall see the calculation of crystal field stabilization energy in octahedral complexes. We know that in case of octahedral complexes, in the spherical field, all the 5 d orbitals will be having the same energy. This is in case of spherical field. Spherical field. And when the ligands are approaching the central metal ion in definite positions, in case of octahedral complexes along the axis, the orbitals will get splits into two sets. That is, the orbitals that are facing the approaching ligands directly, that is dx square minus y square and dz square orbitals will experience more electrostatic repulsions and their energy will get increases, and those two orbitals will form the set of higher energy, and that will be indicated as Ag. And the remaining 3 orbitals, that is dxy, dyz and dxz orbitals, will not experience the so much of interelectronic repulsions compared to Eg set of orbitals. Therefore, their energy will get decreases. That is the orbitals dxy, dyz and dxz orbital, and this set will be indicated as T2G. And this is the energy center, that what we call as barycenter, that indicates the energy value of the spherical field. Provided in spherical field, the energy of the orbitals will be taken equals to 0. And compared to the spherical field, the energy of the T2G set of orbitals will be decreased, and compared to spherical field, energy of the Eg set of orbitals will be increased. And the difference in energy between these two sets of orbital will be taken equals to crystal field splitting energy or crystal field stabilization energy, and is suffixed with O, indicating octahedral complexes, and that's exactly equals to 10 dq. And here the energy of each orbital of Eg set will be increased by a factor of 6 dq, and the energy of each orbital of T2G set of orbital is decreased by a factor of minus 4 dq. Negative sign is indicating decrease in the energy. Or else we can mention in terms of delta naught also, the energy of each orbital will be lowered by a value of minus 0.4 delta O, and the energy of Eg set of orbital will be expressed in terms of delta naught as plus 0.6 delta O. So that energy of Eg set of orbital will be 0.6 times of delta naught. Energy of T2G set of orbital will be minus 0.4 times of delta naught. So that is the energy parameters for the crystal field splitting in case of octahedral complexes. And now we shall see the calculation of crystal field stabilization energy for each and every type of configuration, that is for the distribution of electrons in the d orbitals in crystal field. And we know that if you consider any configuration, the electrons are tend to accommodate in the lower energy orbital first, and after filling the lower energy orbital, then the electron will goes to higher energy orbital, that is according to Aufbau principle. And when we are having the energy of orbitals of same energy, then Hund's rule will be followed, that is each orbital should get one electron at the first, then only pairing should takes place. So by following these two rules, so the electronic distribution will happen in case of the d orbitals of different energy, that is between T2g and Eg. And here you can notice each electron entering into the T2g set of orbital will get stabilized by a factor of 0.4 delta naught, and each electron entering into Eg set of orbital will be destabilizing by a factor of 0.6 times of delta naught, or you can mention in terms of dq also. So by keeping these 2 points in our mind, we can use a quantitative procedure for the calculation of crystal field stabilization energy, that is by the usage of a simple formula according to which the crystal field stabilization energy CFSE, that is exactly equals to N of T2g, that is number of electrons present in T2g set of orbitals, and the magnitude of energy of each orbital is minus 0.4, and plus the number of electrons in Eg set of orbital into energy of each electron will be 0.6 times, and the whole thing is multiplied with delta O. So this is the simplest formula we can use for the calculation of crystal field stabilization energy. And you should notice here the value is minus 0.4 for T2g orbital, and here it is 0.6 for Eg orbital. And now we shall consider the individual type of D configuration, for which we shall try to calculate the crystal field stabilization energy. Now let us consider the D1 configuration, and we shall calculate the crystal field stabilization energy for the D1 configuration, that is the complexes in which the central metal ion is having D1 electronic configuration. So now we shall go with crystal field splitting. So here the octahedral field, this is Eg and this is T2g, this will be the barycenter. So here D1 configuration. So when we are having D1 configuration, obviously the energy, the electron first will enter into the orbital of lower energy. So here the value of E will be 0 for barycenter. So first the lower energy orbital, that is T2g, will get filled. So only one electron is present, therefore that one electron will goes to T2g set. And we are having the formula CFSE is equals to N number of electrons in T2g orbital multiplied with minus 0.4, and number of electrons present in Eg set of orbital multiplied with 0.6 times of delta naught. Therefore CFSE, that's equals to, there is only one electron into minus 0.4, and there is no electron in Eg set of orbital, therefore this whole term will become 0. So no need to mention, or else let us write it as 0 times of delta naught, and that will give minus 0.4 delta naught, or else you can also write it as minus 4 dq. That is the crystal field stabilization energy for D1 configuration. So similarly we shall go for the other configuration, that is D2, D3, D4 and so on. Now we shall go with D2 configuration. So for D2 configuration, let us accommodate the electrons in the crystal field. So Eg and T2g, and this is our barycenter, that is E is equals to 0, and this is Eg, for which the energy is plus 0.6 times of delta naught, and for T2G the energy value is minus 0.4 times of delta naught, and this will be our delta O, or we can also write it as 10 dq, right? So we are having D2 configuration, means we are having 2 electrons. So first the electrons will enter into T2G set. So here 1 electron, then by following the Hund's rule the second electron will go to the next orbital. So only 2 electrons are there which are occupied in T2G set, for which we shall calculate the value of crystal field stabilization energy, CFSE, that is number of electrons in T2G set into minus 0.4 plus number of electrons in EG set into 0.6 whole multiplied with delta O. And here number of electrons in T2G set is 2 and multiply with 0.4, and no electrons in EG set, so the whole term will become 0, therefore delta O. So 4 2s are 8, that is minus 0.8 times of delta naught, or minus 8 dq. That is the calculated value of crystal field stabilization energy for D2 configuration. But the actual value of crystal field stabilization energy for a D2 configuration, by considering all the crystal field effect, that is splitting of d orbitals and interelectronic repulsions, the actual value of crystal field stabilization energy, CFSE actual, the actual value of crystal field stabilization energy for a D2 configuration is found to be minus 0.6 delta naught, or minus 6 dq. This is the actual value of crystal field stabilization energy for D2 configuration. Since we are having some anomalous nature compared to calculated and actual, so this is very important for the competitive examination, so do remember this. And similarly we shall calculate now for D3 configuration. So if you come for the D3 configuration, again we shall see the splitting of d orbitals. This is T2G, sorry, EG, and this is T2G, having D3 configuration. This is our delta O. Fine. So now we shall accommodate the 3 electrons. So 1 will be here, 2 will be here, and 3 will be, and no other electron is present. So T2G set is exactly half filled, and for which we shall calculate the value of crystal field stabilization energy. So the number of electrons in T2G set is 3, and the energy value of each electron of T2G set is 0.4 times of delta naught, and for this it is 0.6 times of delta naught. So minus 0.4, and no electron is present in EG, therefore the second term will become 0 times of delta naught. So 4 3s are 12, so minus 1.2 delta naught, or it will be minus 12 dq. That is the crystal field stabilization energy for D4 configuration. So till now it is much simple for the calculation of crystal field stabilization energy, because we got up the electrons only in T2G set and only 3 electron is present. And now the real thing will start. The exact problem is starting from D4 configuration. So now first we shall show the crystal field splitting. This is EG and this is T2G, and our problem is with D4 configuration. This is our delta O, this is EG, and this is T2G. Energy factor is 0.4 delta naught, energy factor is 0.6 delta naught. So now the problem is, here we have 4 electrons in the D subshell. The problem is, there are 2 possibilities for the distribution of electrons. That is, these 4 electrons can completely accommodate in T2G set, or after filling 3 electrons in T2G set, the 4th electron can go to EG set. So this is the 2 possibilities. So for which we shall write the electronic configuration like this. So for first set, that is all the 4 electrons going to T2G set. So T2G, all the 4 electron will go to T2G set, and EG will not have any electron, that is EG0. And the second possibility is the 3 electrons will first go to T2G set and the 4th electron may go to EG set. So these are the 2 distinct electronic configurations possible for D4 configuration. But one question that arises in our mind, when does this particular configuration will comes into picture and when about this? And this factor is completely depending upon the pairing energy of the electron and its comparison with the crystal field stabilization or crystal field splitting energy. That is, if the crystal field splitting energy, that is delta naught, may be greater than the pairing energy of electron or less than the pairing energy of electron. So there are 2 possibilities. So first point, what is pairing energy? Pairing energy is each and every electron is in need of certain definite amount of energy in order to pair up with the electron which is already present in the orbital, so as to reduce the repulsive interaction between them. And such energy required by an electron is called as pairing energy. So let me say once again, the amount of energy needed by the electron to pair up with the electron which is already present in an orbital is called as pairing energy of that electron. So as I said, the pairing energy of the electron may be greater than the crystal field splitting energy or less than the crystal field splitting energy. So depending upon whether the delta naught is greater than pairing energy or less than pairing energy, these 2 configurations will comes into picture. So when the delta naught is greater than pairing energy, that means the pairing energy is less, that means very less amount of energy is enough to pair up the electrons. In such case, the 4th electron will get paired up in the T2G set. Suppose if delta naught is less than pairing energy, that means the energy difference between the EG set and T2G set is very less, then the 4th electron will jump into EG set. That means when delta naught is greater, that means the energy difference between T2G set and EG set is more, the pairing will occur in case of T2G set, means electron cannot goes to EG set that much easily. But when delta naught is less than pairing energy, that means pairing energy is more, but the crystal field splitting energy is very less. That indicates very less crystal field splitting. In that case, when all the 3 electrons were accommodated here, due to less energy difference, the 4th electron can goes to EG set. In that case, we will get this kind of configuration. So that the pairing of electrons in T2G set or jumping of electron to the EG set completely depends upon the magnitude of the crystal field splitting. That means the crystal field splitting will be dependent upon the nature of the ligands approaching the central metal ion. That means when a ligand approaches the central metal ion, if that causes greater crystal field splitting, then the jumping of 4th electron to the EG set is not possible because of greater energy difference. It will pair up in T2G set itself. When the approached ligand causes very less crystal field splitting, then the energy gap between T2G set and EG will be very less. Therefore, the 4th electron can easily jump into EG set. So, by considering this, in crystal field theory, one limitation of valence bond theory was ruled out, that is differentiating the ligand as a strong and weak ligand. So here we can say the ligand which causes greater crystal field splitting will be called as a strong ligand, and the ligand that causes very less crystal field splitting will be called as weak field ligand. So which is not actually explained by valence bond theory, can be easily explained on the basis of crystal field theory. So now we shall come back to the calculation of crystal field stabilization energy for D4 configuration. So when the electron got paired in T2G set itself, then there will be the electronic configuration distribution will occur in this way: 1, 2, 3, fourth electron got paired here. But if you come to the case of this configuration, now we shall observe the distribution of electrons: 1, 2, 3, 3 electrons in T2G set and 1 electron in EG set. And here you can notice there are only 2 unpaired electrons, and here we have 4 unpaired electrons. That means in case of large crystal field splitting, that is when delta naught is much higher, we will be getting a complex consisting of very less number of unpaired electron, and such complexes are called low spin complexes. And here we can observe greater number of unpaired electrons are present due to very less crystal field splitting energy, and such complexes are called high spin complexes. And now we have to calculate the crystal field stabilization energy for both low spin and high spin complexes starting from D4 configuration in case of octahedral field splitting. So now first we shall calculate the crystal field splitting energy for low spin complex, that is CFSE, that's equals to number of electrons in T2G set is 4. So 4 into minus 0.4, and no electron is present in EG set, so the second term is 0 delta O. So 4 4s are 16, that is minus 1.6 delta O, or you can mention it as minus 16 dq. Okay, so here if you come to the case of high spin complexes, so we are having 3 electrons in T2G set. So 3 into minus 0.4 plus there is 1 electron in EG set, so 1 into 0.6 whole multiply with delta O. So 4 3 is a 12, so minus 1.2 plus 0.6 times of delta O, and that finally gives minus 0.6 delta O, or minus 6 dq. But here if you come to the case of low spin complex, especially here you can notice we don't have any pairing of electrons, but here we have one electron pair, which is already one electron pair, so that here it needs pairing energy. So while mentioning the crystal field stabilization energy for a low spin complex, we should mention the magnitude of pairing energy also. So for minus 1.6 delta naught, we should add the pairing energy. For one pair, we should mention one magnitude of pairing energy, that is P. So this is the actual way of representing crystal field stabilization energy for a low spin complex of D4 configuration. So similarly, we shall observe for 2 more configurations of octahedral complexes. Now we shall see the crystal field stabilization energy for a D5 configuration in both low spin as well as in high spin complex. So 5 electrons. So here low spin in the sense delta O will be greater than P, and for high spin delta O will be less than P. So 5 electrons. So delta O is greater than P. So the pairing will occur in lower energy orbital itself. So first 1, 2, 3, 4, 5. So all the 5 electrons have been accommodated in T2G set itself. So if we come to the case of high spin, since delta O is less than P, so first the electron will singly occupy in both the sets, then the pairing will take place. So 5 electrons, 1, 2, 3, 4, 5 electrons are there. So in case of high spin complex. So now we shall calculate in for low spin and high spin complexes. So first CFSE for a low spin complex. So there are 5 electrons in a T2G set. So 5 into minus 0.4 plus no electron in EG set. So the second term will be 0 times of delta naught, and that's equals to 5 4s are 20. So therefore minus 2.0 times of delta naught, or you can directly mention minus 20 d cube. And if we come to the case of high spin complex, there are 3 electrons in T2G set. So 3 into minus 0.4 plus 2 electrons in EG set into 0.6 times of delta naught, and that's 4 3s are 1.2 plus 6 2s are 1.2 times of delta O, and that gives 0. So that means crystal field stabilization energy of D5 high spin complex is 0, and for D5 low spin complex is minus 20 dQ. With that, the lowering in the energy of central metal ion will be called as crystal field stabilization energy. So greater the lowering, more will be the stability of the complex. So here for a D5 configuration, compared to the high spin state, the complex is more stable in low spin state, which is clearly explaining by the value of crystal field stabilization energy. And now we should mention the value of crystal field stabilization energy for a low spin D5 configuration by introducing pairing energy also, because here in high spin complex we don't have any pairs, but here we have 2 pairs of electrons. Therefore the exact value of crystal field stabilization energy will be minus 2.0 times of delta naught plus 2 magnitudes of pairing energy, and that is about the crystal field stabilization energy of D5 configuration. And we shall do D6 configuration at the last for crystal field stabilization energy. Now we shall calculate the crystal field stabilization energy for D6 configuration in both the form, that is low spin and high spin state, and these are the conditions for high and low spin. So for D6 low spin, so 1 2 3 4 5 6, all the electrons have been accommodated in T2G set. So the electronic configuration will be T2G6 EG 0. And if you come to the case of high spin, 1 2 3 4 5, there is one more electron that again come to the lower energy state and get pair up here. So this is the electronic configuration for low spin and high spin, for which we shall write T2G 3 plus 1, 4 electrons are there, and in EG set there are 2 electrons. So now for this thing we shall calculate the crystal field stabilization energy. So CFSE is equals to, there are 6 electrons in T2G set, so minus 0.4 plus no electron in EG set, so it will be 0 delta O. So 6 4s are 24, that is minus 2.4 times of delta O, or you can mention it as 20 minus 24 dQ. And if you come over here, so CFSE is equals to, so 4 electrons in T2G set, 4 into minus 0.4 plus 2 electrons in EG set, therefore 2 into 0.6 times of delta O, that is 4 4s are minus 1.6 plus 6 2s are 1.2 times of delta O, and that gives minus 0.4 delta O, or minus 4 dQ. So it is crystal field stabilization energy for the high spin D6 configuration. But if you come over here, in case of low spin complexes, we are supposed to express the value of crystal field stabilization energy by adding the pairing energy also. So here you can notice there are 3 pairs of electrons. So one point comes to our mind, that is the value of crystal field stabilization energy is supposed to be add up with the 3 magnitude of pairing energy, that is 3p, but it is not actually. The actual value of CFSE is minus 2.4 delta O plus 2p itself. So one doubt, here there are 3 pairs, but why we are mentioning as 2 magnitudes of pairing energy? Here you can notice, in case of high spin also, there is 1 pair of electron. So in whatever the way, there is possibility of 1 pair of electrons in high spin also. So apart from that, 2 more extra pairing are happening in case of low spin. So for these 2 only pairing energy will comes into picture, and thus we are mentioning as 2p only, not 3p. So like that we can calculate the crystal field stabilization energy for all the remaining configurations of octahedral complexes. Now we shall go with calculation of crystal field stabilization energy of tetrahedral complexes. We know that the splitting of d orbitals in tetrahedral complexes is exactly the reverse in case of compared with that of octahedral complexes. So here compared to the spherical field in case of tetrahedral complexes, the energy of the dx square minus y square and dz square orbitals will be lowered by a factor of minus 6 dq or minus 0.6 times of delta t, where t refers to the tetrahedral complexes of, delta is crystal field splitting energy. And the energy of T2 set of orbitals, that is dxy, dyz, dxz orbitals have been increased by a factor of 4 dq, that is 0.4 times of delta t. That is the energy values of the orbitals of T2 and E set of orbitals in case of tetrahedral complexes. And here in case of tetrahedral complexes, the electron entering into E set of orbital will stabilize the complex by minus 0.6 times of delta t, and the electron entering into T2 set of orbital will be destabilized by 0.4 times of delta t. So here also the same concept will comes into picture, the lowering in the energy of the transition metal ion due to accommodation of the electrons in the d orbitals of different energy in crystal field. The stability of the complex can be easily calculated, and the same rule what we applied in case of octahedral complex, the same thing can be applied for tetrahedral complexes also. And we know that compared to octahedral complexes, the energy difference between the 2 sets of d orbitals in tetrahedral complexes is very less, and we said delta t is approximately equals to minus 4/9 times of delta O. So the energy difference between the 2 sets of d orbitals is very less compared to that in case of octahedral complexes. Therefore, in tetrahedral complexes, we won't observe any low spin complexes, all are high spin complexes only. That means no concept of pairing energy will come over here in case of tetrahedral complexes. And now we shall try to observe the calculation of crystal field stabilization energy in case of tetrahedral complexes for various configurations. For the calculation of crystal field stabilization energy in tetrahedral complexes, we can use this simple formula. The number of electrons in each set of orbital and the energy of each electron will be minus 0.6 times of delta t, and number of electrons in T2 set of orbital and the energy of each electron entering into T2 set of orbitals will be plus 0.4 times of delta t. So this formula can be simply used in order to calculate the crystal field stabilization energy of any configuration in tetrahedral complexes. So firstly, we shall consider the simplest one, that is D1 configuration. So for which the D1 configuration, the splitting can be shown like this. So this is T2 and this is A set with respect to the spherical field for which E is equals to 0. So there is only one electron. So the one electron will goes to the lower energy set first, that is E set. So by using the formula, So CFSE is equals to, and here 1 into minus 0.6 and second term is 0 times of delta T, that's equals to minus 0.6 delta T or minus 6 dq. Similarly, for a D2 configuration, you can calculate the crystal field splitting energy or crystal field stabilization energy by showing the energy distribution, electronic distribution. So there is only one electron over here. So the electronic configuration, we can write it as E1, T2, 0. And for D2 configuration, only two electrons are there. One electron will be here and the second electron will goes to the next orbital according to Hund's rule. So the electronic configuration will be E2, T2, 0. So now we shall calculate the crystal field stabilization energy, CFSE. Two electrons in E set, energy of each electron will be minus 0.6 and no electron in T2 set, so the second term will become 0 whole multiplied with delta T. 6 2s are minus 1.2 times of delta T or minus 12 dq. And the most problem, like in case of D4 configuration of octahedral complex, the problem will arise with the D3 configuration of tetrahedral complexes. So now the possibility here, the T2 set and E set, and here for symmetrical field E is equals to 0, D3. And as we said, in case of tetrahedral complexes, no low spin complex will be observed. Therefore, first electron will be dx square minus y square, second electron will be here, and third electron directly goes to T2 set. And for which we can write the electronic configuration, that is E2, T2, 1. This is the electronic configuration, for which we shall calculate the crystal field stabilization energy. There is 2 electrons in E set into minus 0.6 plus 1 electron in T2 set plus 0.4 times of delta T. Therefore, 6 2s are 1.2 plus 0.4 times of delta T, that will give minus 0.8 times of delta T. But here you can notice, in case of D3 configuration, we observed instead of pairing over here, it went on to the T2 set. So here we should consider the concept of field splitting and interelectronic repulsion, that is the field effects supposed to be introduced. So by considering the field effects, the value of 0. that is crystal field stabilization energy, which came as a 0.8 times delta T based on the calculation, is actually not the exact value of crystal field stabilization energy. The actual value of crystal field stabilization energy for D3 configuration of tetrahedral complexes will be minus 0.6 times of delta T. This is for D3 configuration, and the same kind of configuration will be observed for D8 configuration in tetrahedral complexes. And in case of octahedral complexes, we have said for D4 configuration, for D2 configuration, we have seen the same kind of variation in the crystal field stabilization energy. So in case of octahedral complexes, for D2 as well as for D7 configuration, the value of crystal field stabilization energy will comes as 0.6 times of delta naught and not 0.8. So you can calculate and check up, and this is the way the calculation of crystal field stabilization energy for the octahedral and tetrahedral complexes. So hope the video is useful for you people, and if you know how to calculate the crystal field stabilization energy for both octahedral and tetrahedral complexes and the way of introducing the pairing energy factor in case of low spin octahedral complexes, it is possible to score a good marks in competitive examination if any question came from this particular topic. So if you feel the video is useful for you, please like it, share it, comment it, and do subscribe to my channel. Press the bell icon so that you will get the notification for any update in my channel. Thank you very much.